For our second problem on review worksheet 2 in chapter 12, a great problem with the Lagrange error bound. It says you've got log of x, find a Taylor polynomial, degree 2, centered at c equals 10, also find the remainder, then use your polynomial to approximate what the log of 10.01 is, estimate your error by means of that Lagrange error bound. So, tell you what, we are centered, of course, at 10. We've got f of x is going to be the log of x, which, by the way, is also the natural log of x divided by the natural log of 10, if we changed our base. But, of course, we need to find out what f of 10 is. F of 10 is simply a 1. If we take our first derivative, again, working off of that natural log of x over ln of 10. ln of 10 is a constant. Derivative of natural log of x is 1 over x. So we'd have 1 over x, but of course we've got this 1 over ln of 10. Remember, you plug in where you are centered, and you will have 1/10, and down here you'd have the ln of 10. Let's go ahead and take our next derivative, our second derivative. We know that the derivative of 1 over x is negative 1 over x squared. And we still have this little constant of ln of 10 out there. So when we plug in our 10, 10 squared, of course, is 100. So we'd have negative 1 over 100 ln of 10. It's easy to stop here. However, if we're asked to do the Lagrange error bound, and you're working with that second degree polynomial, you actually have to go one step further. Now the derivative of negative 1x squared, realize that's really, or negative 1 all over x squared. It's like negative 1 times x to the negative 2, kind of like this up here. And you bring down your negative 2, it becomes a 2, and then this becomes x to the negative 3. So hopefully you can see quickly, you'd get 2 over x cubed. By the way, you still have this little constant of 1 over the natural log of 10. By the way, here is where you don't plug in your 10. Remember, we plug in that very obscure and abstract concept of z. So, we're asked to make our polynomial, and that's for part A. And hopefully you can know that this second degree polynomial, if we write it out in just pure theory, this is f of 10 plus f prime of 10 times x minus 10 to the 1 plus f double prime of 10 times x minus 10 to the 2 all over 2 factorial. And at this point we can clean it up. We can very simply say, well, f of 10 we just saw was 1. We saw that right here. F prime of 10, of course, was 1 over 10 natural log of 10. And we've got our x minus 10 right here. Almost done, by the way. This f double prime of 10 we just saw is negative 1 over 100 ln of 10. But 2 factorial brings another 2 down below. And I know this is negative, so let's just clean this up real quickly. We'd have minus 1 over 200 ln of 10, and then we'll have x minus 10 squared. That, guys, is the first part of what we were asked to do, to make a second degree Taylor polynomial. But notice that we're also asked to make the remainder. And the remainder, please understand, is going to be the third derivative evaluated at z, and we'll have x minus 10 to the third power divided by 3 factorial. So what is this thing? Well, we just saw that f triple prime of z was this 2 over z cubed ln of 10. 3 factorial, however, is also going to be there, so you could pull this out in front if you'd like. And then you could say, well, then you also have this x minus 10 to the third all over 3 factorial. we know that 3 factorial is actually going to be a 6. It's also 3 times 2, but look, your 2's would cancel out. So if you wanted to clean this up pretty quickly, you could. You'd get x minus 10 to the third all over 3z to the third, natural log of 10. But with this very important note that z is between where you're centered, which is 10, and x. So this is what we have for our error. Now, for the sake of time, just to make this video a little bit shorter, they ask you in part B to estimate what the log of 10.01 is. So the log of 10.01 is about roughly what we get when we plug in 10.01 into this polynomial at the top of the screen, this thing right here. So I'm going to leave it to you guys to confirm what I've just worked out as well. I've got that right next to me. I've already typed it out. But you can see that that is roughly about 1.000434 and so forth. And that's remarkably close to what you'd see on the calculator anyway. But the next question is, let's talk about error. Well, your error, this is where this is newer material, and I'd like to break that down just a little bit more. For our error has to be less than the Lagrange error bound. So remember, we're plugging in 10.01. So we'd say 10.01 minus 10 to the third all over 3z to the third, natural log of 10. And again, this time we can get even more specific. Z is actually going to be between 10 and 10.01. So we don't know exactly what z is, but we do know that z is in this denominator down here. And we're trying to maximize the error. We're trying to do a worst case scenario. And when we can say that our error can't be any worse than this, we actually have an error bound. Because z is down below, this fraction is going to become biggest when this z value is smallest. So look, even though I don't know exactly what z is, we're going to choose z to equal 10 to maximize our error. We want to make that denominator get as small as possible. So in other words, our error is going to be less than, well, 10.01 minus 10 is just your 0.01 to the third. And down here we'll have 3, 10 to the third, natural log of 10. So here's where I will show, the punching out step by step. We can definitely just get alpha y equals up here. The top we'll say is 0.01 to the third. Down below we're going to say 3 times 10 raised to the third. Move that down, then say multiply that by the natural log of 10. Notice that you no longer really need those absolute values. This is all positive. But you can see what we're getting. 1.44764 times 10 to the negative 10. That's your error bound. So you can say that your error is actually remarkably small from the Lagrange error bound. So just some more practice with this skill. It's a little bit abstract, but hopefully it's getting better for you.